In this video, I'm going to go over the formulas that you should have come up with when doing investigation for 10.6 and go over some examples of how to use those formulas. So first, I'm going to go over the formulas that we already know for angles in a circle. When you have a central angle, the vertex is at the center. And the central angle is equal to its intercepted arc. When you have a vertex on the circle, there are two ways that can happen. You can have an inscribed angle, like we talked about in the last sections, or you can have an angle made from a tangent line and a secant line. Here, in each case, the angle is equal to 1/2 the intercepted arc. You can have angles where the vertex is inside the circle, but not the center. This can be made by two secants or two chords intersecting. In this case, if these are my angles, notice those are vertical angles, so they would be congruent to each other. These are the intercepted arcs. So we're going to look how to find the measure of those angles in a little bit. And then we can also have where the vertex is outside the circle, and that can happen in three ways. We can have two tangents intersecting outside the circle. When that happens, we get two intercepted arcs. This one and this one. We can have a secant and a tangent intersecting outside the circle. When that happens, we get three arcs. The two inside the angle are the intercepted arcs. Or we could have two secants intersecting outside the circle. When that happens, we break the circle up into four arcs, but once again, only two of them are inside the circle and are inside the angle and are the intercepted arcs. So these were the ones I was asking you to investigate for your 10.6 investigations. You were looking at a secant tangent like this one, and then these and this, trying to get the formulas for all of those. So we're going to start with the intersecting inside the circle. So in this particular case, I asked you to look at a triangle. I made a triangle for you. And I hoped that you remembered, back when we were talking about triangles, that the exterior angle, angle 1, was equal to the sum of the remote interior angles, angles 2 and 3. Then we can see that the measure of angle 2 is equal to 1/2 its intercepted arc, because angle 2 is an inscribed angle. Its intercepted arc is right here. So it's 1/2 the measure of arc BC. The measure of angle 3 is equal to 1/2 its intercepted arc, because it's also an inscribed angle. Its intercepted arc is ED. So by plugging those in, I can say that the measure of angle 1 is equal to 1/2 the measure of arc BC plus 1/2 the measure of arc ED. Factoring out that 1/2 gives us 1/2 the measure of arc BC plus the measure of arc ED. Notice that BC and ED are the intercepted arcs for angle 1 and its vertical angle. So we can say that the formula for when two secants or two chords are intersecting inside a circle, the formula for those angles is that it's going to be 1/2 the sum of the two intercepted arcs. So that's the formula that we have up here. These two angles, angle 1 and its vertical angle, are equal to 1/2 the sum of these two arc measures. Angle 2 and its vertical angle are equal to 1/2 the sum of these arc measures. So when doing problems like this, the first thing that you need to do is whatever angle you're trying to find, you need to figure out what its intercepted arcs are in order to use the formula. The first thing you want to do is figure out what formula to use. So you ask yourself, where is the vertex? In this case, the vertex is inside the circle. So we're going to use the formula that we just came up with. The intercepted arcs for angle X are this one and the one in the vertical angle. I don't know those measures, but I know that all four of these arcs add up to 360. So I can do 360 minus 143 minus 75, and that's going to equal the measure of arc AC plus the measure of arc BD. And since X is equal to 1/2 the sum of those two intercepted arcs, once I find that sum, I can just divide that by 2 to get what X is. So 360 minus 143 minus 75 is equal to 142. And so the measure of X is 71 degrees. In this one, again, the vertex is on the circle. This time we want this arc. So we're still going to use the same formula. The measure of the angle is equal to 1/2 the sum of the intercepted arcs. I'm going to go ahead and put the intercepted arcs in the formula. GH and KJ. So the angle measure is 110. I can plug that in. The measure of arc GH is X. That's what I want to know. And the measure of arc KJ is 97. The best way to solve this equation is to multiply both sides by 2 instead of distributing that 1/2. Because if I distribute that 1/2, I'm going to get a decimal or a fraction that I don't really want to work with. So if I multiply both sides by 2, I get this, and then 220 minus 97 is 123 degrees. All right, the second part of your investigation, you were supposed to look at the secant and tangent line that intersected on the circle. So that's important that the vertex is on the circle. And hopefully you found that when you measured this arc and that angle in Sketchpad, that the measure of angle B was 1/2 the measure of its intercepted arc, BC. So just like the inscribed angles where the vertex is on the circle, these secant tangent angles where the vertex is on the circle has the same formula, that the angle is going to be 1/2 the measure of the intercepted arc. So you could use that for these next investigations, plus the fact that our triangles, that the exterior angle is equal to the sum of the remote interior angles. So I'm going to use that again here for the secant tangent angle. The measure of angle 3, the exterior angle, is equal to the sum of the two remote interior angles, 1 and 2. Now, I want the formula for angle 1 because it's the angle where the vertex is outside the circle. So I'm going to rearrange this to get that the measure of angle 1 is equal to the measure of angle 3 minus the measure of angle 2. Well, the measure of angle 2 is an inscribed angle. EC is its intercepted arc. So it's equal to 1/2 the measure of that intercepted arc. The measure of angle 3. Angle 3 is one of those secant tangent angles we just talked about, where the vertex is on the circle. So it's equal to 1/2 that intercepted arc, or arc BC. So when I plug things in here, the measure of angle 3 is 1/2 the measure of arc BC. The measure of angle 2 was 1/2 the measure of arc EC. Factoring out the 1/2, we get this. Notice that BC and EC are the two intercepted arcs inside of angle 1. So here we get the measure of the angle when the vertex was outside the circle is equal to the difference of its two intercepted arcs. We scroll down to the tangent. We have the same equation. Angle 3 is our exterior angle, and 1 and 2 are the remote interior angles. Rearrange that so I'm solving for the measure of angle 1, the measure of angle 2. Angle 2 is one of those secant tangents, so it's equal to 1/2 its intercepted arc. Angle 3 is also a secant tangent, so it's equal to 1/2 its intercepted arc. Now I want you to notice that in this particular case, the 2 intercepted arcs make up the entire circle. That's important when you have tangent-tangent angles. You only need to be given the measure of one of these arcs, and the other one is going to be 360 minus that. All right, so back to this equation. When we substitute those things in, the measure of angle 3 was 1/2 the measure of arc BEC. The measure of angle 2 is 1/2 the measure of BC. Once again, we're going to factor out the 1/2, and we get that that measure of the angle where the vertex is outside the circle is equal to 1/2 the difference of its intercepted arcs. And this last case, same equation, measure of angle 3 is equal to the measure of the remote interior angles added together, angle 1 and angle 2. Rearrange. Measure of angle 2 is equal to 1/2 its intercepted arc because it's an inscribed angle. The measure of angle 3 is equal to 1/2 the measure of its intercepted arc because it's an inscribed angle. Substituting those in, we get this, factoring out the 1/2. Once again, we get that the angle with the vertex outside the circle is equal to 1/2 the difference of its 2 intercepted arcs. So first, we're going to look at problems where we have that secant tangent where the vertex is on the circle. So anytime the vertex is on the circle, whether it's an inscribed angle or secant tangent angle, the angle is 1/2 its intercepted arc. There's only one intercepted arc. In this problem, we're looking for this angle right here. The intercepted arc for that angle goes from A all the way to where it touches the circle again at B. So the measure of angle ABC is equal to 1/2 the measure of arc ADB. Well, I don't know the measure of arc ADB, but I do know that this arc and the given arc make the entire circle. So I can figure it out by subtracting from 360. To get 258. divide that by 2 to get 129 degrees. Anytime the vertex is outside the circle, as we saw with the investigations, the angle is always equal to 1/2 the difference of its two intercepted arcs. What you need to do is figure out which ones are the intercepted arcs. When you have a secant, these two are the intercepted arcs, the two that are inside, not the two that are outside the angle. When you have a secant tangent, these two are the intercepted arcs, again, the two inside the angle, not the one outside. When you have a tangent, the entire circle makes up the two intercepted arcs. So here I have my secant. The very first thing I want to do is see where the vertex is outside the circle. So I know my formula is that it's going to be 1/2 the sum of, or the difference of its intercepted arcs. Then I need to find the intercepted arcs, AE and BD. So I know that X is equal to 1/2 the measure of AE minus the measure of BD. Notice that it's always the farther arc minus the closer arc, so that you don't get a negative answer. So AE is 120, BD is 50, that's 70, so X is 35 degrees. In this one, we again have the angle measure, so we're still going to use the same formula for outside the circle, but this time we know the angle measure and we don't know either of the intercepted arcs actually. So what we need to do first, this is a tangent, so the two intercepted arcs are the X, the thing that I am looking for, and the rest of the circle. Since I don't have an expression for that, I can call that 360 minus X. So now I know that the measure of angle S is equal to 1/2 the measure of arc PQR minus the measure of arc PR. PQR is my 360 minus X. PR is my X. And this is 11. Again, we want to multiply both sides by 2 rather than distributing. This 360 minus X is the same thing as 360 minus 2X. So if I move this 2X over here and do 360 minus 22, I get 2X equals 338, and X equals 169 degrees. Here, angle Y is outside the circle, so I know that the measure of angle Y is equal to 1/2 the difference of its intercepted arcs. WRV is one intercepted arc, and ZV is the other intercepted arc. Now I know the measure of ZV, but it's 10x, so I need something to plug in here. So we have to notice a diameter right here. This is the diameter of the circle, which makes this a semicircle, which makes that 180 degrees. Now I have enough to plug in to be able to solve for x. The measure of angle y is 45. The measure of arc WRV is 180. And the measure of arc ZV is 10x. Multiplying both sides by 2. And we end up with x equals 9. So just to recap again, all the new formulas that we learned. When the vertex is on the circle, either as an inscribed angle or a secant tangent angle, the angle is equal to 1/2 the measure of the one intercepted arc inside that angle. When the vertex is inside the circle and not the center, that angle and its vertical angle are equal to the sum of the intercepted arcs. In fact, we're averaging equal to 1/2 the sum of the intercepted arcs. So we're averaging these intercepted arcs to get that measure of angle 1. When the vertex is outside the circle, your angle is going to be equal to 1/2 the difference of the two intercepted arcs. So again, anytime you are trying to find the measure of an angle that's related to a circle, figure out where its vertex is so you know what the formula is. Figure out what the intercepted arc or arcs are for that angle, and then plug those things into the formula and solve for the rest.